In the following part of LS10, we're going to take a look at a separate example by designing a 4-bit equity comparator. The exact purpose of a 4-bit equity comparator is to compare two 4-bit binary numbers, and the output is a single port saying whether they're equal or not. So if the two 4-bit numbers being inputted are equal, then the output would be 1, or else it would be 0. Step 1 specification specifies the input and output. On the input side, we have two 4-bit numbers, A and B. The different digits are denoted using subscript, so it goes from A sub 3 to A sub 0 and B sub 3 to B sub 0. That is a total of 8 different ports. On the output side, we have only one single bit, and this one single bit is E. E equals 1 if A equals to B, and E will equal to 0 if A does not equal to B. In the next step, we're going to go directly into formulation. The formulation of this particular problem is going to be a little bit different to your usual truth table. It is unreasonable to do a truth table for an 8-digit input, just too much stuff happening over here. And the specific nature of this design demands a simpler solution, since we're just comparing two numbers to see if they're the same. In this particular case, two different things are going to happen. What we can do is we can compare pairs of binary values and see if they're equal. Say A sub 3 is compared to B sub 3. A sub 2 is compared to B sub 2. A sub 1 to B sub 1 and A sub 0 to B sub 0. If any of the pairs are different, then the output will be 0. But if all of them are equal, then we're going to output 1. So we can divide and conquer this. We can do pairwise comparisons and then combine the comparison results of all these different bits to make up the final answer, E. So what is essentially happening is we've divided a slightly more complex problem into an easier one by doing comparisons in pairs first, whether they're the same or not, and then produce E. This essential idea is called a hierarchical design, which is similar to what you would find in algorithm design terms in your programming language studies, something called divide and conquer. Sometimes when you're faced with a situation of having to design something more complex, a complex circuit, the circuit design is broken up into individual functional pieces, also called functional blocks. Each block will have their own explicitly defined interfaces, such as inputs and outputs, and their own input and output mappings, the behavior or truth table, or specification, if you like. The basic idea is once you design all of these different pieces, or each of these individual functional blocks, the blocks can be reused multiple times to make your final design process a lot simpler. If a single block itself is too complex, of course you can further divide it into smaller blocks so that you can design them easily. Slightly more easily, I guess. So, what can happen in our specific case is when we're trying to design the 4-bit equity comparator, we can define two different components. First of all, we can define a component named MX. MX will be in charge of comparing pairs of values. And then we can design a separate piece called ME, which combines all of the results for pairwise comparisons to finally compose E. And here is the rough shape of what it looks like. As you can see, the MX component will be comparing only pairwise results. And again, because MX will only need to be designed once, and then we can reuse the same design everywhere else as a functional block, just like you would an AND gate or OR gate or NOT gate. You no longer need to be concerned with their internal designs. If it's designed properly, it will always work. So, first of all, you would do pairwise comparison using the MX units, and then all of the outputs from the MX units are being fed into the ME unit to compose the final output E, to determine whether they're all equal or not. So, let's divide this labor into further blocks. So let's take a look at MX first. MX is going to have its own truth table. The ideal thing to do over here is to follow the 5-step systematic design procedures for the MX unit and ME unit separately. Now, for reasons of time, we're going to shorten this up by directly giving you the answer to compare A sub I and B sub I, and determining if they're equal or not. We're going to define the output N sub I to be 0 if they are equal, and 1 if they're not equal. If you do that, you'll quickly realize that the only component you need is actually an exclusive OR gate. You can simply use exclusive OR gates to design the MX unit. Alternatively, you can also just use standard AND or OR components, depending on whether the exclusive OR gate is part of the technology available to you. So let's say the exclusive OR component is not available to you. What you can do is you can simply implement this Boolean expression using standard components, the AND, OR, and NOT gate, such as this. Once you have implemented the MX unit, you will need to turn it into a subcomponent, the video of which is shown, the tutorial for which is already on the course website. This is LS10 part 2, the tutorial for creating a new part in LogicWorks so that you can reuse it every other time. The next thing you will need to do once you've created MX is you will need to design ME. ME is going to combine all of the N values to make up the final representation. What you can do is, again, N sub I is going to equal to 0 if they're the same. So the only case where E is 1 is when all of the inputs N sub 0, N sub 1, N sub 2, and N sub 3 is 0. So we can implement that using N sub 0 or N sub 1 or N sub 2 or N sub 3, and then a big negation on top. So that is the essential idea of a hierarchical design. Let's take a look at how to implement it in LogicWorks. For this particular tutorial, I've actually created a new library, as you can see over here. To do so, you can go to File, Libraries, and then create a new library. As you can see over here, if I go to my library, it does not contain anything from previous teaching. Let's start with this. First of all, let's design the MX unit. The MX unit is essentially an exclusive OR gate. That's all we need. So let's bring out an exclusive OR gate. Because we're basically, we need to turn it into a part, we're going to need some ports. Let's go to a library. This is under Pseudo Devices, or you can also search for it in the filter. Let's go get our port ins for input. We're going to need 2 of them, one named A. You can name it A sub I or A, just depending on what you like. I'm just going to call it A. The other one B. This is going to be your input. On the output side, you're going to need port out. You can see the port out is facing the wrong direction, so you will need to flip it horizontally to make it pretty. Connect it. give it a name. This is n. Like we said before, you can implement mx in this particular manner if you do have an exclusive OR gate available to you. And in this case, I've actually skipped the verification step, but in practice, you should always check for connections and check if this design actually works using binary switches and probes first. In this particular case, let's try to implement the same circuit without using the exclusive OR gate. Again, let's delete the exclusive OR gate and corresponding wires. If we want to implement this without using exclusive OR gate, you will need an OR gate. Go to all libraries and find yourself an OR gate. Two AND gates with one invert to make things simple. The first one is going to take A, not B. Make sure it's connected. Graphical glitches can be resolved by scrolling up and down. This should be B. And over here below we have not A, and B. Like I said, it's not always easy to make it pretty, but we do our best. Now let's connect it up. Ideally you should be testing it, but for the sake of time I'm going to skip that. And also you should be saving this as, for example, an MX unit. We can do that very quickly by saving this as MX. In my folder, this is located under my LogicWorks folder. I'm going to save this. The next thing I'm going to do is, just like the previous tutorial, LS10 part 2, I'm going to go to File, New, Device Symbol. And in this case, I'm going to Options, Subcircuit and Part Type, create a subcircuit symbol, select an open circuit to attach to it, select MX. OK, done. You see all of the ports on the left hand side. Drag a little box. Inputs on the left hand side, output on the right hand side. And don't forget to name this thing. And you're done. Save it as new component inside your library. Don't try to save it in some of the system libraries. It will make things confusing. Save it in my library as MX unit and then save. Now if I go to my library, I'll be able to see this MX unit inside. Let's create a new circuit. Now we can just drag out 4 different MX units. For the ME unit, since we're not going to reuse it multiple times, I'm just going to implement this over here. But for the input, I'm going to need, let's use 2 hexadecimal keyboard. One for A, one for B. And again, to use the hexadecimal keyboard, you want to use the one without SDB port. Let's give them some names. This is A, this is B. Oops, this is B. And always remember the most significant digit is on top. What we can do over here is we can just establish the connection by doing the connections by hand. This is not the most elegant solution. As you can see, it's actually going to take up quite a lot of space. And it's just the same value being carried around. Not quite very elegant. And you will need to do the same thing for B as well, which is also going to take up space. Let's do that. and there's an overlap. We need to prevent overlaps so it's easier for us to see. And there we essentially have it. We have connected it. Make sure to check for connections and check this is the least significant digit. They need to be aligned with the least significant digit of A. These two as well, these two as well, these two, well, these two as well. Always check all of your connections. But I guess you can see the primary problems over here. When you're doing this kind of connection, sometimes it gets very confusing, which is why you can use something called a bus to help you mitigate this problem. Now, bus essentially just gets rid of all of these wires and carry values on a single thick wire, like this over here. A single bus over here can carry as many digits as you want. And in our particular case, we'll be carrying 4 bits of digits from one location to another. To be able to utilize buses to do that, first of all, we're going to need to go to schematics, new breakout. And let's just call our pins D sub 0 all the way to D sub 3. You can do this by following the example over here. If you declare D sub 0 to D sub 7, this is 8 bits. If you do D sub 0 to D sub 3, this is 4 bits, because 0, 1, 2, 3, these are 4 numbers. You will also need to specify a pin spacing, but remember when we're discussing this, we have told you to try to keep the spacing between 2 ports pins at 2. So this will make all of the buses look very nicely. And all of these buses, let's flip it horizontally, they can be directly attached to any of our existing components. On the right hand side, we can create equally spaced ports that get mapped to these different A's and B's. We can estimate their spacing by this is 2 spacing, this is probably another 2 I'm saying, another 2, another 2, so I'm guessing that's probably 8 apart. Let's create a new breakout, D sub 3, 0 all the way to 3. This time, spacing 8. That's actually correct. Let's flip it horizontally. You can see this bus has its values split equally between all of the A's. And all we need to do is just to connect the buses together. And it will correctly forward this particular value to this wire. This value to this wire. Basically D sub 3 to D sub 3, D1 to D1, D0 to D0. We repeat the same steps for B. Let's create a little bit more space over here. Let's try to connect all of the B's. And then connect the wire, thick wire. And there you have it. This way, it makes it a lot easier to spot mistakes and to spot connections. Well, correct connections, hopefully. The next thing we're going to do is we're going to design the ME component, which is just combining all of the ends. What we're going to use is we're going to use NOR gate, 4-input NOR gate to be more exact. Connect all of them. This is essentially your ME component. And finally, we need only a binary probe. Give it a name on the wire, E, and we can start testing our circuit implementation. Let's say the 2 inputs, if they're the same, then E should be the same, so 5 equals 5, that is the same. 5 does not equal to 6, so this is no longer the case. We can repeat that. A equals A. 5 does not equal to A. 5 does not equal to 7. The only case where E is positive is when A, the value over here, the value over here equals to the value of B over there. That concludes our example over here. One other cool thing about using buses is that if your bus carries indeed a number, what you can do over here is you can right click on this bus over here, give it a name. Let's say this is the value of A, this is the value of B. When you change the values, say over here, this is 0, this is 0, let's give it 3 and 3, and you try to zoom in on the timing diagram over here, you'll actually be able to see these individual values. 5 was the first value we provided, and then 0 and 3, and you can see the value of E is also changing accordingly, albeit with a tiny little bit of delay, that is.